Okay, everybody, welcome to 5th and 6th grade science for week 27. Yes, week 27. Welcome. How's everybody been? I hope last week you guys enjoyed your Zoom meetings with your teachers. I know we were all really looking forward to that and being able to see you guys, see you face to face, video to video, to see your faces. It's really fun. We miss you guys, and it's been fun to be able to connect like that. So I hope that everyone enjoyed that. And if you didn't get a chance to join your class meetup, try again this week. On the big Google Drive that you get all of your lessons and supply forms, that's where those links are. So if you have any questions, you can check with your teacher. But try to plan to do that next week. So the first thing we're going to do right now is I need you to get out your piece of paper and a pencil. And let's just do a quick review of what we learned last week. So I have gotten a lot of really good feedback from your water cycle experiments. Thank you for doing those. I would say probably 99.9% of you had those supplies available to you at your house and or wherever you are and could do that experiment. Now, if you haven't yet and you just watched it, try it. Do a little science lesson for your family and let them know what the water cycle is like. We talked last week in my video about how interesting it is, and actually it's kind of makes it fun from a science perspective to study weather and climate right now during the spring, because I don't know if you've been kind of watching the weather outside, but it's been kind of crazy. One day it's beautiful and 60 degrees and warm, and you go out on the grass and it's great, and 15 minutes later the sky is black and the wind is blowing and it's 20 degrees. Okay, maybe not 20, but it's colder. Then it's warm again. Then it's pouring rain. Last night here where I live, in fact, yesterday's weather was a perfect, I should have done like a time lapse of the whole day. It started out kind of cold in the morning, and then it warmed up. It was wonderful, and the sun was out, and I could hear people out mowing their lawns and edging and doing some work outside because it was beautiful. Then all of a sudden I looked outside, the house got dark. It was dark outside, and the wind kind of came up, and it was this really weird black cloud. No rain or anything, just this black cloud kind of blew in, and then the sun came back out, and then it started to rain. And it sort of rained enough. That kind of rain that gets your car dirty, but not like pouring down rain. And then it kind of stayed like that for a while, and then it just poured, and then it was beautiful again. So the temperature went up and down and up and down. So watching weather and climate during the spring is great, especially here in Utah. So we're going to talk a little bit more about Utah's climate here in just a second when we get our video started, or when we talk about our lesson. But as we're working with weather and climate, once you understand the water cycle and why it works the way it does, and why we see the results of the water cycle in our weather, it kind of makes it a little more interesting. So hopefully you've done that experiment, and if you have, I'd love to see a picture, or at least like a quick explanation of what you found, what your findings were. So that was last week. Now this week, as we still stay with weather and climate, hang on, I gotta move you around so I can see. And we've been having a little bit of technical issues. That's why I came back up here to the school, so that I could make sure that everything went smoothly. So everyone, be crossing your fingers. So if I asked you to tell me the difference between weather and climate, now I think I've used both of those words when we just did a quick review. Could you tell me a definition about weather and climate? So with your piece of paper, I want you to take it, and you can either do it this way, or you can do it this way, and either fold it or draw a line. But I want you to write weather on one side and climate on the other. Like we're going to use this for an experiment in a minute, so that's why it's already folded. But weather and climate. So go ahead and write weather, and then climate. And I want you to write down a definition, what weather is, and then what climate is. Give yourself a second to think about that. If you had to guess. Are they the same? Are they interchangeable? What's the difference? Why would one use, weather and talk about weather, and why would you use climate and talk about climate? If you need 1 second, just push pause, But if you've got some notes down and you kind of have a basic understanding, let's go ahead and continue. I'm going to show you a video, and it is going to let you know exactly what the difference is between weather and climate. There's a car outside the window. If we were doing a science lesson on sound, it's so loud. His radio is so loud, it's vibrating the window. So you can think about that science principle for a second while we're queuing up this video. Okay, so with your piece of paper and your definition, your ideas about the difference between weather and climate, as you're watching the video, I want you to make a couple of notes. I want you to write down how weather and climate are defined exactly and what those differences are.
Have you ever wondered what climate was like on Earth hundreds or thousands of years ago? This is the same question that scientists are asking. So one way that they can look into the past is by studying ice cores from glaciers to get an idea of what the climate was like so many years ago.
What's the difference between weather and climate?
Weather is basically the hour-by-hour, day-to-day changes that we see. You go on TV and you watch the weatherman to see what it's going to be like in a few hours, maybe even towards the end of the week. Climate is basically the overall average of what happens in an area on a scale of years or decades or centuries.
I see. So, weather looks at one day, while climate looks at the average of many days. Now, this average tells us what it's normally like at a certain place. Let's take a look at Forks. No, not that kind of Forks. Forks, Washington. From 2003 to 2009, it rained an average of 117 inches a year. Now this tells us that it's normally rainy in Forks, Washington. Now let's compare this to Las Vegas, Nevada, where the average annual precipitation is only 4.13 inches. We can see that the climate in Forks is wet and the climate in Las Vegas is dry. Now that we understand how to determine climate, how do we find out what the climate was like on Earth hundreds or thousands of years ago? This is where glaciers come in. What is a glacier?
A glacier is basically snow that has accumulated over many, many years. It will drop down and it will stay there without melting, and it will just continue to snow year after year after year, piling up on top of itself. And as those accumulations occur, enough snow and ice will start to build up. So it starts off as snow at the top, but then turns to ice at the bottom after so long and with enough pressure.
Let's say that this bowl is a mountain basin. The first year there's a light snowfall. The wind blows dusts, pollen, and other things found in the atmosphere onto the snow. The next year there's a heavy snowfall, and the volcano of a neighboring mountain erupts. The top layer of snow and ash adds pressure to the layer below. The weight of each new snowfall compresses the layers of snow below it, turning the older layers at the bottom to ice. This is how glaciers form. What do glaciers record?
The glaciers are going to record year-to-year changes. There's all these sorts of things that we can look for within the glacier to see what the atmosphere was like, how many greenhouse gases were in the atmosphere at this time. They can also look at dust to see how dry or windy a place was at that time. Pollen. Was it wet? Was it dry? We can actually even see bomb testings, volcanic ash. They can see volcanic eruptions that occurred. This kind of information can really help us look into the past and look at climate and what the atmosphere or the climate around that region was like.
Where are glaciers found?
Surprisingly enough, you can find glaciers all throughout the world. When people think of glaciers, they automatically think of the Arctic or the Antarctic, which is true, there are glaciers there. But people don't normally think that the tropics are areas that are going to have glaciers, but in fact they do. India in the Himalayas, in South America, and there are even glaciers on Africa, like Mount Kilimanjaro. You just have to go high enough up into the mountains where the snow is actually going to fall and accumulate. It's important to study several different locations rather than just one, mainly because the scientists want to get an idea of what's going on globally. So if we're going to look at the climate of the Earth in the past, we can't only go to one location. Something might have happened there that didn't happen elsewhere. We need to go to several different locations and then use the information that's found there to sort of bring it together so we can see exactly how the climate has changed on Earth as a whole. So what we've learned today is how a glacier can really give us a look into what the climate was like on Earth so many years ago. Many scientists are trying to use this information and collect it before it disappears, so they can see how Earth's climate has changed over hundreds or thousands of years.
All right, good video. So there's a lot of information in there. Let's get back to us. Hello. All right, so get your paper out. Hopefully you had your first rough ideas of how you might define weather and climate, and then let's go over what she talked about in the video. So weather and climate, how are they different? So with weather, we're talking about the hour by hour or day by day changes in the state of atmosphere. So what is the weather like? We're talking about what is it like right now? Is it, so for me, if I looked outside, there's no way you guys are going to be able to see that. That was worth a shot. What's the weather like? It is actually beautiful. I'm going to check. We're going to ask. Okay, so we're in Kaysville. It's 50 degrees. It is full sunny. Throughout the day, it's supposed to reach a high of 63. Yay! That's today, the day that I'm recording. And it's supposed to stay sunny all day. However, tomorrow, lightning and thunder. So when I talk about the weather, and then throughout the week, it'll be sunny and then rainy and sunny and then rainy. See, Utah, spring weather. Excellent to study. If we were filling out forms, you'd have a lot of data there to study. So weather is the day by day or hour by hour changes in your surroundings in the atmosphere. So that's weather. You could look at it over just a day, a week, and she said, you know, just kind of your like certain period of time. Then what is climate? So the way she described climate was it's the average of the overall changes in weather. So it's the state of atmosphere over an extended period of time. So if you were, let's break it down for Utah. So we know that Utah's weather is typically, and we could, you know, find out what the, you know, summers are warm and hot. Autumn is, you know, mild, windy. Winter is cold and snowy. You could pick your, you know, spring is nutso. Wet, rainy, sometimes snowy. We call it like third winter, sometimes in the spring. It's crazy. But climate, if we were going to look at someone who's going to come and visit here, they would say, what's the climate like in Utah? And you could look over an extended period of time and find those averages. So the average temperature in the summer is blank. Or in the winter, and it snows this many days, and it rains this many days, and it's, you know, over 100 this many days in the summer. That's climate. So in even longer, an extended period of time, over hundreds of years, this is what the climate is like in Utah. So there's a good definition to separate what the difference between weather and climate. Now, how do they get those averages? How do they find out climate over an extended period of time? What was it that they study? Glaciers. I loved the way they explained the glaciers too, in that there's glaciers everywhere. And we just think about it sometimes, you know, way in the tundra up in the north, but they're they're able to check the data from those glaciers in many areas. And don't you think, just like in any science, that you're going to need to check the data of several different areas over a long period of time to get the real data, because something could happen crazy. She gave the example of, you know, it'll snow, and then whatever was happening in that area, she talked about a volcano or pollen, or, you know, something may have happened here, but it didn't happen, you know, over in this part of the world. And then as that packs down and then it snows again on top, and the pressure builds up and builds up until it forms ice at the bottom. And when they study those glaciers and those layers, they're able to tell, you know, based on what is in between, what's pressed in between, what may have happened. And that's how they find out a lot of different things about what's happened in the past, is by studying glaciers. So I thought that was really good, interesting information. So now that you know a little bit about weather and climate and glaciers, let's talk about what causes weather changes, and that is airflow. So when we talked last week about the water cycle, it brought up how the air pressure and the airflow, you know, it's changing. My chair wiggling around. Whoa, I'm off camera. It talks about, we talked about what happens with the wind and how the wind, the airflow and the air pressure changes, and that affects the water cycle. It also affects the weather. So let's do another quick video, and it's going to show us all about air pressure. Okay, it looks like I'm having just a little bit of trouble with this video. Let's try one more time. So isn't technology fun? Okay, let's try this again.
What I've been thinking about lately? Hanging out on a tropical beach with sand between my toes and a cool breeze blowing through my hair. I mean, strictly in the interest of science. Because the breeze in my hair and the wind and even the big cycles going on out there in the ocean are all great ways of understanding currents. A few episodes ago, we learned that the uneven heating of land and water creates wind by forming different pressure zones. The air above the land is warmer and less dense, so it rises, and the air over the water is cooler and heavier. The cool air rushes in toward the low pressure zone over the land, forming a lovely sea breeze. But you may have noticed you don't need a beach to feel a breeze. Nope. Wind is everywhere. Air is constantly moving all around the world in cycles or currents. Sometimes they're small, like a light breeze blowing off the sea, and sometimes they're massive, mighty rivers of wind. Let's see how currents move around the world. You know the Earth is a sphere, so the sun's rays hit the middle of the Earth straight on. This part of the Earth receives direct sunlight. Meanwhile, Earth's poles receive indirect sunlight, or sunlight coming in at an angle. Here, the light is spread out over a larger area and is less intense. This means the Earth's equator is much warmer than the poles. I mean, you wouldn't pack a swimsuit for a trip to the Arctic. And you know that when we have differing temperatures, we're going to have different pressure zones. The area around the equator is a low pressure zone. Here, the warm air rises and starts to slowly move towards the poles. Now, if the Earth weren't spinning on an axis, and if it didn't tilt, and if it wasn't covered in water, then the warm air at the equator would just rise toward the poles and the cool air would move in at the equator, where the warm air just left. This would create two giant air currents called cells. But, of course, things on Earth are much more interesting. The sun hits the equator, causing warm air to rise, and the air moves away from the equator, but it doesn't have time to get all the way to the poles. About a third of the way, the air cools, falls, and moves toward the equator again, creating a smaller cell. Another cell is created in the mid-latitudes and another at the poles. In each cell, cold air sinks and warm air rises. There are 6 of these cells circling in the Earth's atmosphere. And at the boundaries of these cells, something really weird starts to happen. We get jet streams. What? Air in these cells is trying extra hard to get from one pressure zone to another, since there's a big temperature difference between the air over the poles and the air over the mid-latitudes. But the Earth is spinning faster at the equator than at the poles. If you were to stand at the Earth's axis on the North Pole, you would spin around more slowly than if you were standing on the equator. So, as air rises over the equator and makes its way toward the poles, it keeps moving eastward at the same rate, even though the higher it goes, the slower the Earth is spinning. This creates ribbons of very fast-moving air called jet streams. Jet streams move in wiggly patterns across Earth caused by the interaction with other high and low pressure systems, and also also with seasonal changes too. These streams are usually between 6 to 14 kilometers off the ground and can reach speeds of 442 kilometers per hour. Simple enough. But of course, there's more. We know from our little trip to the beach that there are other factors here. Remember our nice sea breeze? Those small differences between high and low pressure caused by the heating of the land and water taking place on all the coastlines around the world. This makes air patterns even more complicated. And jet streams and wind patterns aren't the only currents flowing around the world. Water actually moves a lot like air. Warm, light water rises and cold, salty, heavy water sinks. And just like with air, the sun heats the water that's at the equator, and that warm water then spreads out toward the poles. Cold water slowly moving back down toward the equator where it'll warm again in an endless cycle. This massive movement of water, called ocean currents, helps regulate global temperatures just as much as air circulation. All of this interaction between the land, air, and water creates some pretty complicated wind, weather, and climate patterns. These currents make large parts of Earth livable. Without them, the poles would be far too cold and the equator scorching hot. So, currents are a little complicated and messy, and they're always on the move. They're caused by uneven heating of the Earth's surface, whether that's between land and water or between the poles and the equator, and they're all driven by energy from the sun. Without that energy, our air and water would be still. And all of these complex currents blowing and flowing around all over the place makes it really hard to predict where the wind will blow, and therefore, what kind of weather you're gonna have next week. But that's a problem we'll explore in another episode, and until then, I'm gonna keep planning my beach vacation.
There we go. Okay, so that was a lot of information about air currents and air pressure. So if we had to just kind of get the nuggets, I thought that was really interesting. And any of us that have been out on a beach, we know that feeling 100%, where the heat of the heat difference between the ocean and land causes those winds. Haven't you ever stood on the beach and you feel that breeze come in? So what we know about air pressure and air currents is she likened it, an air current, to a river of wind. So that is kind of a cool visual. And it's caused by areas of high and low pressure. So based on where you are and what the temperature is, it's going to change the pressure. So over land, air is warmer and it's less dense. So that air is going to rise. And then over the ocean, she kind of described it as like heavier, saltier water, but the water is more dense, heavier, and it's cooler, so it's going to drop. I thought the visual that she showed us with the Earth, with the little cells, so that there's 6 cells, I thought that's really interesting. And where we live in North America, and especially, kind of in Utah, we get those jet streams that come in from the ocean, and they come in over California and blow our weather in all the time. So we're really familiar. If you guys watch the weather tonight, wherever you are, hopefully, like we said, it's spring, there's probably something crazy going on. But listen for some of those key terms, with the currents and where the jet stream pops through, and, it comes up and brings us either, cold air or warm air. But I thought it was a really good explanation of currents in the jet stream and those different cells. So one thing that we wanted to kind of explain today is a little bit about air pressure. And there's 2 different experiments that you can do to kind of give you an idea of air pressure. And they're based on I think he's from Sweden. Let me just peek really fast. I think he was a Swedish, it doesn't even matter. His name is Bernoulli, and this is Bernoulli's law. And the way he explains it is let me read it to you, because it's good when I read it correctly and not try to guess. But his theorem, or his law, states that energy is conserved in a moving fluid, liquid or gas, and if the fluid is moving in a horizontal direction, the pressure decreases as the speed of the fluid increases. So if the speed decreases, the pressure increases. So for example, water moves faster through a narrow portion of a horizontal pipe than through a wider portion. So Bernoulli's principle predicts that the pressure will be the lowest where the speed is the greatest. So there's 2 different experiments that you can do it to kind of see how that works. I'm going to show you the video of the first one. If you guys have 2 balloons at your house, you can hang them up. I did right here. As you can see, you see our balloons hanging right there. So when we watch the video, it's going to try to give you a visual of what happens when you blow between those two balloons. What's going to happen? What the air pressure changes? What would you predict would happen? And then once you blow on it, and you can practice kind of blowing, it's just an experiment. You can blow fast, you can blow slow, but it's the change in the air pressure. We can do that one in a second. So let's watch the video together. It's this one that you were looking at. There we go. Okay, I love those Teach STEM videos. I think we've used a couple. Anyway, I really like those. I like those experiments. So you can do this experiment one of two ways. You can do it with two balloons and the string, or you can do it with two paper cups. We may not all have balloons hanging around our house, but you may have a paper cup. A plastic cup isn't going to work. If you don't have a paper cup or a balloon, can you think of something else that you could use? Something that would give you an example of, two things that you could hang, and then when you blow, you're blowing the air through the center of where those two were hanging. And then what was your prediction? What did you think was going to happen when he blew the air? Mine was immediately, if you just think about it, oh, they're going to go apart super fast. But what happened? It was the same. Let's see. So here's our tent. We got our tent of paper. So I would have thought when we blew, maybe like that, that the paper, that the paper wouldn't automatically flatten. I think my first instinct is that it would probably pop off the desk, but it immediately flattens. Now, we know that that's because the air pressure, when you blow through, the air pressure going through the tent is lower than the air pressure on the outside. And what happens with when the air pressure is lower, it's going to cause that heavier pressure to push down, and it's going to flatten. So it's the same principle. Bernoulli was the scientist's name. It's the same principle with the two balloons. So if you can do that experiment, test it out. If you blow really fast, if you blow slow, you could use a straw, you could use a toilet paper tube to maybe direct the air a little more, but see what happens to those two balloons when you Should we try? I've tried a couple of times and there's so much static here. It must be like in me and in the floor that those balloons, they move around a lot. So hold on. Let's set it up. All right. So I may have them just a little too close together too now that I'm looking at them. Let's separate them just a hair. All right. So it said maybe about like that. So right now they're really good and they're staying where they're supposed to be. So if I blow, did you see how they immediately went together? So I think this would be a really cool one if you had something to direct the air, like a toilet paper tube or a paper towel tube maybe, or you could even make one out of a piece of paper. But can you guys see one more time? See how they're drawn together? Hello. So the air pressure then, because the air pressure is lower between them, they immediately like suck in together. All right, let's go back. If you were to do that with, two paper cups, I would suggest trying maybe like the lightest ones that you can find. Styrofoam ones would be great, but kinds that you use for hot chocolate. But you could also try that with two regular plastic cups. And then if you think of something else that you could use where you could have the air pass between them, that would be pretty cool. So that's the experiment that you can do with air pressure. I have one last experiment that you guys can just watch. This isn't one that you will do as a class, but it's one that you can watch, and it's a Bill Nye. So let's get him pulled up and you guys can watch and kind of get an experiment of, it reminds me a lot of the one that we did last week. Okay, in this last video, Bill Nye is going to give us a little explanation of what it's like with the air movements around the poles. So I think this is a really good visual of what the second video showed us about the way that the wind works between the poles, like the cold poles and the warmer equator. So let's watch Bill Nye. Just kind of get a visual on that one. Maybe.
The science guy. Bill Nye the science guy. Wind all over the world is caused by heating and cooling of the earth. Wind can do work, and it makes sailboats go. Well, he went right through the door. Now, real wind doesn't come from a fan. No, in nature, wind is caused by the heat from the sun and the rotation of the earth. That's what makes these intricate patterns of clouds that we see on this photo from space. It works something like this. This is our great big plastic wind box of science. These lights represent the sun. This ice represents the north and south poles. So here's what happens. Energy from the sun heats the land, and the land warms the air over the land. The air molecules get going faster. They spread farther apart, so they don't weigh as much for the room they take up. So cold air can push the warm air up. That's why we say warm air rises. So look what's happening. The smoke shows us that the air is sinking over the cold poles, blowing over the cities, and then rising over the warm parts. See, it goes around in a great big circle. And that's what happens on the Earth. Now, there's one more thing. The Earth is spinning, so the wind starts spinning. That's why wind comes from all different directions. Wind is wild.
All right, wind is wild. So I thought that video right there explained everything we just talked about perfectly. I love to see things like visually. I need to be able to see it, and that's really cool. So you could see anybody that's been to San Francisco or Seattle or some of those cities where you see that happen and it's kind of foggy and it comes it comes in, and then when it gets over land, it raises. So that's kind of a really fun visual. So you guys, I hope that you have learned a little bit more about air current, air pressure, jet streams, how those affect the weather. What do those have to do with the weather where we are? The difference between weather and climate when we're talking about what the weather is like, and then what the climate is in any given place. We talked a little bit about what it's like here in Utah. How they predict, or how are they able to know hundreds of years ago what things were like, and what they used to study climate is glaciers. They are glaciers. So I think we've hit all of the top points. I'd love to know if you were able to do the Bernoulli experiment with your balloons or paper cups. I'll have both of those supplies listed on the additional supply sheet. And then if you can think of any of their experiment or pictures or observations of how this works with weather and climate, I would love for you to share those with me. So make sure that you guys do your homework for do that little experiment, see if you can get your family involved in it, try a couple variables and see what you think, and then just be prepared for next week. We'll talk a little bit more about weather and climate. Make sure that you guys go to your classroom Zooms this week so your teachers can see you. Hopefully that you'll be able to make that. And then I hope you all have a great week. I'll talk to you later.